This time we are going to do a somewhat larger example to illustrate the naive Bayes approach. So first of all, we are going to use a data set that is contained in a package called MLBench. Okay, so your first step is going to be to install this package MLBench so that we can use a data set that it contains. Okay, so I've commented this line out, but you should run this. Okay, now the data set that we are going to use from this is called House Votes 84. Okay, this is from the US Congress, and in the year 1984, how did various members of Congress, members of the House, vote on various issues? That's what this contains, right? So we've got several issues, I think 15 or 16 issues. On each issue, we've got information on whether a person voted yes or no. Okay, now if you look at the possibilities for every issue, every person can vote yes or no, and therefore the number of possibilities is enormous. It is 2 raised to the power of 16 or 17. I think there are 17 issues. So it's a big number. So obviously the data set is not as big. The data set is much smaller. I think it's only about 200 and something, as 300 something, as many members of the House as there are. Okay, so it's a small number. Okay, so obviously not enough to cover all the possible cases, right? So what we are going to do in this example is to build a model given a person's voting record to predict their party. Are they Democratic or Republican? That's what we're trying to do. Okay, so it's a complete classification problem. All the attributes are categorical, yes or no. So this is perfectly suited for naive Bayes. Okay, so you can do view House Votes 86. This is what it looks like. Okay, so you've got the first column has the party of the person, which is our target attribute, Republican, Democratic, and these are all the various issues. There are 16 issues, V1 to V16. Okay, and for each issue, you know what the issue was, right? So if you go to the description of V1, we'll see, this was what to do about XYZ, and what was the vote that the person had, yes or no, on that particular issue. Okay, so here are all the things. So for example, second, some bill concerning handicapped infants. So the senator can either vote, the congressperson can vote yes or no. Or waste project cost sharing. Some, again, you could look at the actual bill and the person voted yes or no. This is what you have. Okay, so what we want to do is to, given the votes that a person had in Congress for a particular issue, see if we can predict what their party was. Okay, of course, this doesn't have any future or any practical application, but it's a good illustration of how naive Bayes can work and what kind of problem it is suited for. Okay, so again, we're going to do the partitioning of the data. As always, we're partitioning 70-30. Okay, that's just before. And then initially, let's do the default cutoff and make a prediction. Okay, so HV, housevotes.nv, is naive Bayes class tilde dot, meaning predict the target attribute called class based on all of the other attributes, V1 to V16, data equals train. Okay, so we've got the model. I'm not looking at the actual model. And then we are saying now, let's generate the predictions on the training partition. Predict hv.nb comma train. So predict pred.train contains, we can now generate the error matrix. Actual equals train dollar class, predicted equals pred.train. This is the predictions. Actual is contained in the data frame. So we generate the error matrix, and the error matrix comes out like this. Okay, so clearly, at least on the training partition, the model does a fantastic job of prediction based on, based on the attributes. Okay, so it's able to predict Democrats quite well and Republicans extraordinarily well. Okay, now let's do on the test partition, pred.test, and performance is pretty good on the test partition as well. Almost as good as on the training partition. Very, very comparable, both of these error matrices. Okay, so the model seems to be performing. So now of course, what we did here was using the default cutoff, right? If you just do a regular prediction, by default, it predicts the class, right? So it's going to make a prediction of Republican or Democrat because those are the two classes. It's going to make a class prediction. That's how the default predict works for naive Bayes. If you want to predict probabilities, if you want to do the ROC chart, of course, Then we want to predict probabilities and then determine the cutoff. We want to generate the ROC chart and then determine the cutoff. So let's do that process also. Now, incidentally, in the assignment that I've given you, once again, you'll be using a fairly large data set and you'll be going through all of these steps. Okay, so let's assume that the positive class is Democrat. Okay, again, before anybody accuses me of having a liberal bias, the reason I'm choosing Democrat as a positive class, it allows us to illustrate label ordering, right? Otherwise, label ordering will not be required because Democrat, Republican, by default, Republican will be taken as the positive class. So we don't have to do label ordering. I'm deliberately making Democrat the positive class just so that I can illustrate the need for ordering of the labels. We've looked at it before, but it doesn't hurt to emphasize. Okay, so we're going to do ROC charts, so library ROCR. And first, let's go ahead and now predict probabilities. Okay, so to predict probabilities, I'm saying prob.train is predict hv.nb train type equals raw. Okay, so this is what is going to make it predict probabilities. Again, this particular way of doing it is for naive Bayes only. For every method, you have different ways of getting the probabilities as we've already seen. Okay, and this is what it looks like. The probabilities look like this: Democrat, Republican, and it's showing you the probabilities. Of course, it's showing it in scientific notation because it's got tremendous number of decimal places. What this is basically showing you is that it's 9.9999 E minus 1. E minus 1 is basically 10 raised to minus 1, or basically it's 9.99999 divided by 10, which is very close to 1. Okay, so for the first person on the data set, whoever it was, the system says that the probability is almost 1 that they're Republican. Okay, same thing for the next, etc., etc. Okay, so it has predicted the probabilities. So for this person, it's saying the probability is 1.6 divided by 1,000, right, is less than 0.0, it's a little more than 0.001. Okay, so that's what the predicted probabilities are for somebody to be a Republican or a Democrat. We know how we can use this to generate an ROC chart, right? So we do prediction, and the first argument to the prediction function is the generated probabilities of the positive class. Okay, so I'm saying our positive class is Democrat, so I say 1, first column, right? Remember, the first column contains the contains the probabilities for Democrat, and I'm saying Democrat is our positive class, and therefore we take the first column. And here are the actual classifications, but now we have to tell the system what is our label ordering. Label.ordering is Republican, Democrat. Okay, now if you recall, the label.ordering in the prediction function, the positive class always comes last. Okay, now if we didn't specify this, then by default Republican would have been last, right? Because in terms of alphabetical ordering, Republican would come after Democrat. So that would be the last one. That would become by default the positive class, right? So if Republican was your positive class, then you didn't have to do label ordering, which is why I said, let's make Democrat the positive class so that I have to illustrate label ordering for you. Okay, so this is exactly what I'm explaining here. The highest item by label ordering is the positive class, so we are changing it. Okay, so this set is always the same. Perf, the code is always going to be pred, TPR, FPR, true positive rate, false positive rate, and then plot performance and then lines. So that comes out to be our ROC chart. And of course, the ROC chart is shows very clearly, it reflects the error matrix that we saw, right? That the model is very powerful in terms of predicting, right? So if you took the people with the highest probabilities for being a Democrat, you will find that the system is extremely powerful in terms of being able to predict, right? So you can get a true positive rate of almost 0.7 without incurring even one false positive. Okay, in other words, the top many cases are correct if you went by the probabilities, right? And then to increase the true positive rate some more, you have to start incurring some false positive, right? So you can get your true positive to 1 by incurring a false positive of a little more than 20%. Okay, so clearly this is a very artificially powerful application of naive Bayes. And this is happening because we know that the country is highly politically polarized and has been so for a long time. And people are just voting on party lines on many issues, right? Which is why just looking at somebody's vote on an issue can tell us which party they belong to. That's really what this is illustrating. Okay, so now we want to determine the cutoff, which is very easy really, right? And in order to do that, we generate this textual representation of the cutoff, right? And let's say that we want very high probability, right? So I've chosen to go with this, right? So up to this point, we can get almost a 90% true positive rate while incurring only a 3% false positive rate, right? So here we get a very slight improvement in true positive and a big increase in false positive. I don't like that, so I'm choosing this particular point. So my cutoff is going to be this, 0.96. Okay, so I'm choosing a cutoff of 0.96. And then we can now generate the classifications for the training partition. So again, I'm saying cutoff is 0.96. If the probability is less than cutoff, treated as a negative class Republican, otherwise treated as a positive class Democrat, and then generate the error matrix, comes out like this. Okay, which is that the performance for the positive class has actually deteriorated slightly, but the performance for the negative class has improved significantly. Okay, so that's just the cutoff that we chose. And this is for the test partition. Okay, so if you chose the default cutoff, the error matrix on training looked like this. And if you choose a deliberate cutoff, the error matrix on training looked like this. Like we said, significant good improvement in the performance on the negative class and a slight deterioration in the performance of the positive class, right? For a small decrease here, we got a somewhat more proportionate increase here. Okay, so it improved on the negative class. That is, true negatives improved. And this is the same thing on the test partition. Okay. So that is how you do naive Bayes with ROC.